Hey, Charlie Pyatt here. This time out I'm revisiting the trackball gamepad design I did last year. That project was more about exploring the origin of modern game controller layouts and inputs. Sort of like imagining if Nintendo had taken the N64 controller in a different direction back in the 90s. I learned a lot about gamepad design with that project and wanted to take those lessons and apply them to a new, more modern touchpad controller. I also noticed one or two comments politely asking about Gyro in the comment section of that video, so I thought it would be fun to explore that too. Aside from gyro and touch control, I plan on doing a wireless controller with Hall effect triggers and hot swappable mouse switches for my digital buttons. Finally, I really liked having a mouse wheel for navigating in-game menus and swapping between inventory items, so I'm going to carry that feature over from the trackball controller too. None of these features are particularly revolutionary on their own, but I've never seen them combined into a single controller, so this should be a pretty fun experiment. The goal is to have this new design appear as a separate Xbox gamepad and a mouse on any standard Windows PC. This single controller showing up as two devices is similar to what I did with the trackball project, but in a much more elegant setup. I talked about this a little in the last video, but the controller market is kind of a mess right now when it comes to game inputs. Windows sees human interface devices, or HIDs, in specific categories. You can have keyboards, mice, and gamepads, but each of these inputs can only be seen as an individual device. You can't really have a single controller that is a mouse and a gamepad right now, which means there really isn't any proper support for gyro controllers at the OS level at the moment. There are a couple common workarounds for this problem though. Some games have direct support for gyro controllers, but when they do, it's only for the most popular controllers like the Nintendo Switch Pro and PS5 DualSense. The other main option to get a gyro controller going is to trick the game into thinking a player is using a hybrid input setup to play. Hybrid control is where a player is aiming with the mouse and moving with the analog stick on the controller. If a game supports hybrid input like this, then a driver can be used to convert the gyro signal on the controller to mouse input. Steam Deck and Steam Controller use this method using Steam Input as the intermediary driver for games played on Steam. If this all sounds insanely confusing, that's because it is. The good news is that there are enough large companies pushing gyro out there in 2025 that eventually there's going to be some kind of standardized gyro controller input at the OS level for gaming. It just hasn't happened yet. To kick off my design process, I want to start by figuring out the electronics for my controller. I'm already familiar with the Pro Micro board I used for the Spatial Mouse project, but that just isn't going to cut it for this one. I want something that has low power draw with built-in Bluetooth support and, ideally, an integrated battery controller. Fortunately, there's already a line of chips that do just this in the ESP32. These microcontrollers have good support and are designed specifically for wireless devices. After some looking around, I found the Adafruit ESP32 S3 Feather, which is quite a mouthful. I can develop on this using the Arduino IDE, just like the Spatial Mouse project, and it has built-in Bluetooth support and even includes a battery controller. It also has a bunch of I/O pins for the controller inputs that I'm going to need. Remember, I'm combining a controller and mouse into one device, so this is going to need digital buttons like the ABXY, direction pad, upper shoulder buttons, and start select. Then I need 2 analog triggers and a single stick. Then I need to cram in a mouse wheel and 5 buttons in there. That and the other stuff I didn't even talk about work out to 24 digital pins and 6 analog pins. That's a lot of stuff. And I haven't even figured out my touchpad yet. Found out pretty quick that I wouldn't be able to fit all that on the S3 Feather. Fortunately for me, this is another super common problem that's already been solved with input-output expanders. Found a good I/O expander for my needs in the PCF8575 that will give me another 16 pins and just barely cover all my input needs. It also works over I2C, which I'll talk about more in a bit. So now I have my microcontroller figured out, which covers my wireless needs, battery control, and my input pins. Now I need to find an off-the-shelf gyro module that will work with the ESP32. I went with the MPU 6050 Gyro because of its low cost, availability, and abundance of software support. At this point I started plugging things into breadboards to test out the hardware. If you're new to electronics, breadboards are used to quickly plug in components for testing without needing to solder any of the electronics together. On a standard breadboard, each of these rows is connected by an electrical contact, as well as these long power rails on each side. It makes prototyping and testing electronics layouts pretty quick and easy. My first mountain to climb was figuring out how to make my ESP32 see my gyro and I/O expander over I2C. I2C stands for Integrated Circuit Protocol? That's a horrible acronym. I2C is used for communicating with multiple electronic devices. Makes it so I can attach devices to the same 4 rails, power, ground, clock, and signal, and communicate with each of them individually. This massively simplifies wiring and pin count, and it's how I'll be communicating between my I/O expander, gyro, and other components. Eventually I hobbled together a working I/O expander and gyro along with some test components and an analog stick and a rotary encoder that will drive the mouse wheel. You can see the MPU 6050 gyro acting as an air mouse here, which is already amazing progress. At this point it was time to make some decisions about features. I was toying around with including a touchscreen for configuring the controller in the final design. This would have been amazing, but the level of difficulty is going to be too much for my skill level right now. So the screen was the first thing to hit the chopping block. The final choice was around the touch setup. My first plan for this controller was to have it as a kind of flick stick layout for FPS games where you touch an edge of an input pad and you look in that direction. I thought it'd be fun to use a capacitive touch ring for this, and I found some off-the-shelf hardware to test this idea out. Fortunately, I was getting a lot of noise in the signal and just couldn't get the level of precision I wanted out of it. Eventually I decided just to switch over to a standard round touchpad. This would end up being way more flexible and able to emulate an analog stick or be an additional mouse input trackpad. I found the Circ GlidePoint trackpad that operates at 3 volt, just like the ESP32, and can run over I2C, which is all perfect for my use case. Doing the embedded programming was going to be a massive undertaking for me. The Spatial mouse was really my first serious microcontroller programming project, and that was mainly combining existing open source code examples and libraries. Software to drive the Valence will require a much more complicated code base. In short, it's way over my head. Because of my skill level and this project complexity, I really had to rely on AI programming tools for this one. I tried a few different methods and eventually landed on Claude to do most of the programming work, which worked incredibly well. The ability to ask how things work and talk through development strategies was amazing and made me really enjoy getting the project going. Taken passes at trying to learn everything from C# to Python to even BASIC over the years and found that I just flat out didn't like it. But this was really fun. As far as development process goes, the first thing I had to do was figure out how to set up multiple devices in Windows through a single Bluetooth connection. Remember, this needs to connect to Windows and appear as both a separate mouse controlled by the gyro and a traditional Xbox game controller. Fortunately, there's an existing library that does exactly this called ESP32BLA Composite HID. This library was a lifesaver for me. With a bunch of tweaking, I was able to get Windows to see my custom Bluetooth device, which would appear as an Xbox controller and a mouse HID under the Windows device list. Before I really dive into the CAD work, I need to make my custom PCBs. The way this would usually be done on a normal production controller is that most, if not all, of the buttons, switches, and sticks would be directly mounted on a single PCB. You can see an example of this on the donor gamepad I used for the old trackball controller project. Because I'm not sure how my layout will physically fit together quite yet, I'm not going to do it like this. I'll just keep most of my inputs off the main board and connect them by JLCPCB connectors. This will give me much more freedom and adjustability in where I want to place them in my layout. So the first PCB I need to design is my main one that will mount the ESP32S3, the 8575 I/O expander, and the 6050 gyro. I'm going to treat those as daughter boards that will mount to this main custom PCB I'm designing. I use gullwing headers here so I can solder the components to both sides of my PCB without them interfering with each other. This is not the way you're supposed to use these headers, but I did the same move with the Spatial mouse and it worked really well. The problem with this method is that once the boards are all soldered to those headers, you can't access the header feet anymore, so it's kind of a one-way trip on the assembly front. The main PCB is going to be stacked with those JLCPCB connector ports I already talked about. All of my buttons, stick, hall sensors, and touchpad will connect to this main board through those. These connectors fall into the Micro Surface Mount Device or SMD category of component, which are much more challenging to solder. I've never actually used SMD components before, but this is a project of firsts, so I might as well keep that trend going. The final components I have to get on that main board are my transistor setup to control the rumble motors. These are all SMDs too, so this is going to be a lot of technical work to solder right. With the main board done, I have a couple other boards to do. I need a basic board for the stick that will just act as an adapter from the stick pins to the JLCPCB connector. The last boards to do are the single button boards, the direction pad, and the ABXY board. If you remember back to the beginning, my plan is to use hot swappable mouse switches for all these digital buttons. For that I use these keyboard hot swap barrels. These are little tubes with internal leaf spring type contacts that make an electrical connection with the keyboard switches when they're pressed in place. This lets keyboard switches be pulled and changed without having to resolder anything. I've never tried this, but I'm pretty sure you can use these hot swap keyboard barrels on mice switches too. The individual switchboards will have a couple of these barrels soldered in place, then a single 2-pin JST-SH port to connect to my main board, and a through hole so I can easily mount them to the controller frame. Last thing I have to do is the ABXY and direction pad. These boards will also hold the start and select buttons and used hot swap mouse switches in a kind of unique layout. I'm going to get extra tricksy here and make these flip boards. If you connect the switches on one side and the port on the other, the board will act as an ABXY version. If you flip the board over and mount the switches and port to the opposite sides, it will act as a direction pad board. Amazingly, these all worked out really well in the end. So now I have all my custom PCBs done. I can export the 3D models out of KiCad into Fusion to build around, and also save them out as Gerber files to send away to JLCPCB to be fabricated. That brings me to today's sponsor, JLCPCB. I've always been impressed with how simple JLCPCB makes the process of getting your own custom circuit boards. It's quick, easy, and I get high-quality custom PCBs back fast so I can keep moving with my designs. For the Valence controller, I just drag and drop my Gerber files onto their quoting tool, instantly preview the order, and I can adjust settings with clear explanations. It's simple for beginners, but powerful enough for pros. JLCPCB offers 1 to 8 layer boards starting at just $2, with turnaround times as fast as 24 hours thanks to their 5 advanced fabrication sites. And because everything is handled in-house, from fabrication to assembly, strict quality control stays constant throughout every process. Over 6 million engineers across 180 countries have trusted them with their PCB and assembly needs since 2006. Check out the link in the description below and see how easy it is to get started with JLCPCB today. With my hardware running and the basic code propped up, I needed to switch over to planning the physical industrial design of the controller so I could figure out what kind of space my electronics and custom PCBs would have to fit into. The design of my last trackball mouse controller was meant to have a weird, funky 90s throwback style. For the Valence, I wanted to use more modern design styling. I'm going to play around with an internal lattice frame that will hold my micro components with a snap-on translucent exterior for cladding parts. This will give the whole design some nice visual depth and complexity, but not be too crazy or overwhelming. Should be a nice mix of techie and sophistication. For the trackball mouse, I had to figure out the ergonomics using a clay model because there weren't any existing similar products on the market. In this case though, there's an endless number of controllers out there that I can use as reference forms. With that in mind, I went to my local big box electronics store and tried out a bunch of different controllers to see which one felt the best. Eventually found the SCUF Envision Pro, which has all the physical inputs I needed and felt great in my hands. I'm just going to be 3D scanning the SCUF to use as a reference model for my new controller, so I don't even need a functioning gamepad. Because of that, I went on eBay and found a non-working parts-only Envision Pro for $25, which worked way better for me than the $199 MSRP new one. Next up, I needed to 3D scan the SCUF controller so I can start my CAD work. I just bought a Creality Raptor Pro 3D scanner that really expands the size of objects I can get into CAD. I'm only going to use this scan as a rough size reference to model around, so I really just need a medium to low resolution scan without a crazy high level of detail here. Put some tracking dots on the SCUF and started my scanning process. I just slowly moved around the controller, bringing in the scan data. I usually try and get a few different angles so I can merge the scans together easily. The more overlapping data there is on each scan, the easier it is to merge things together. With my point clouds processed and merged, I can generate my final mesh. This mesh is what I'm going to bring into Rhino to start my surface modeling around. This surfacing step in Rhino will give me the base solid model to import into Fusion for building my parametric CAD. This all gets into the weeds of surface sculpting strategies for industrial design, which is a very technical place to live. In simple terms, I'm using the scan mesh I just brought in to make another type of reference model to use to make my final surfaces. Basically trying to leverage the strength of each type of geometry to get where I want, if that makes any sense. With those steps done, I have a pretty clean finished surface model for my controller. You can see in the zebra stripe view that the surfaces are looking pretty clean. There aren't any major jagged lines or jukes in the stripes at all. The Chrome view looks good too, so I think we're ready to export this as a step file and bring it into Fusion for my final CAD. At this point I have all my digital assets ready so I can make my controller design here in Fusion. I imported my SCUF Envision Pro source scan, which I'm going to use to place my custom PCB assemblies in 3D space. I've also imported my surface model from Rhino that I'll be using as my 3D file to build off of. I need to model some minor electronic components like my trigger hall sensors, glide point touchpad, and battery pack, but those are all simple shapes with detailed schematics that I can pull dimensions from. I already talked about my overall goal for the industrial design and style side of this build. I want an inner frame with a translucent snap-on exterior parts. I'm going to 3D print all these parts, so I don't need to worry about undercuts or any serious manufacturing constraints. As a first step, I'm offsetting the outside of my controller surface model inwards, then splitting it into two bodies with some tolerance left in between. This gives me an exterior shell with the right wall thickness surrounding an internal volume that will eventually become the mounting frame for all my electronic components. Now I'm just working through orienting my PCB assemblies in space. It took a lot of tweaks to get all my switches in place and not overlapping or getting in the way of other components. Fitting everything together is kind of like a complex puzzle at this point. Each one of these little subcomponents has to have a routing path for the wire to the main board. I also need holes through the frame large enough to feed JST SH cables through to connect everything up. Because the controller is a pretty organic form, I have components at weird angles throughout the entire assembly too. I eventually got to a place that I was pretty happy with. All the internal PCBs are secured with 2.5mm screws that just tap directly into the resin frame print. Most of the PCB assemblies are captured between the exterior surface and the frame, so the screws just need to secure the boards in place, not hold up to a bunch of force or anything. The left-right triggers and back paddles were definitely the most challenging things to design here. They had to relate to the existing geometry form, but have enough clearance around them to be able to pivot. I used 2mm stainless steel rod stock as the pivot for all my hinges. Cramming the mouse wheel into the left trigger was also a difficult situation. The parts really started to pack into that area and it was super challenging to get everything to fit. Eventually I got it figured out though. With my Fusion CAD modeling done, I want to do a final pass to the inner frame model where I lightweight it as a lattice structure. This will make it so the inner frame isn't a solid block anymore. It'll save a lot of resin during the print, weigh a lot less, and most importantly look way cooler under the translucent exterior shell. For this I'm going to bring that interior frame part back into Rhino and do these final moves in Grasshopper. This is a process I've developed over a bunch of projects like my EXO custom in-ear headphones, the Stational Mouse, and the custom micropad project. First I'm bringing the inner frame geometry into Grasshopper and doing a triangular remesh on the outside. The new edges of that mesh will be my lattice struts in the final part. From there I'm using the Dendro voxel plugin to do a bunch of Boolean operations. I can make it solid around the areas holding the components and have the rest of the body be a large triangular surface lattice. All that gets output into a single ready-to-print mesh. Now that all my parts are ready, I can start the 3D printing process. I'm using my Form 4 resin printer on these parts with the interior made out of Tough 2000 resin and the exterior in clear. I do my usual post-processing of the parts by rinsing them in isopropyl alcohol and post-curing them. Tough 2000 material works really well for consumer electronics like this. It's super durable and has a really nice surface finish with very little post-cleanup needed. The clear shell is going to take a little bit more work to get the effect I want. For the exterior clear parts, I'm going to wet sand them down to 800 grit and then clear coat them using matte Krylon rattle can spray paint. I find this gets a really nice frosted effect on the finished parts. I also have a handful of black parts that I'm printing. These are mainly the back paddles and wheel. I want to keep the interaction elements as black parts with the digital front face buttons and direction pad as clear so you can really see the inside switches. This will also give a really nice view of the interior lattice frame. My PCBs came in, so now it's time to move on to soldering my first micro-component SMT type project, so we'll see how this goes. I have an older TS100 iron with a standard blunt tip that I've used for a bunch of years. I ended up ordering a new micro chisel tip for doing all these small contacts. I also got a cheap digital magnifying scope that turned out to be a real pain to work with. This thing is really just a digital camera with a small screen and doesn't have proper binocular eyepieces. Turns out working with no depth perception at this scale isn't super fun. In any case, I started soldering the small switch PCBs, thinking these would be the easiest to do and lowest risk if I mess up, which I plan on doing. JST-SH connectors are the hardest parts to get soldered down on these by far. I designed my boards so the ports mount backwards with the pins facing out to make it a little easier to solder. The two pads on either side of the connector are for mechanically securing the port to the PCB and preventing any force on the port from being transferred to the more delicate pins. I found that I could use a dab of solder on those large pads to secure the connector in place, making it easier to do the rest of the pins. Any other way I tried to do these, and it would end up with the ports and pins misaligned on the board and a general mess. I think I had around 30 of these to do, and I figured out that workflow on the 29th one. The flip style ABXY and direction pad boards were pretty easy to do. Just had to remember to solder the barrels and ports on the correct sides for the ABXY button version or the mirrored direction pad version. The main board was the most challenging because of the number of ports, density of components, and higher risk factor if something went wrong. My plan was to work from the center of the board out, so I started by getting those gullwing headers down. To do this, I would cut them to length, tack down the first and last gullwing foot on the board, and then finish soldering those headers in place, knowing that everything would be in alignment. Finally, I would go back and solder the main components into the headers and have the gyro, I/O, and ESP in place. From there I moved on to the GST ports. As I mentioned, I really struggled with these and didn't feel like I had a good flow for doing them until the very end. Probably should have gone back and started over to get better, cleaner connections at that point, but I felt like that would have been lacking in character. After that, I placed the transistors, resistors, and diodes for the haptic feedback motors. These were some of the most challenging soldering parts of the whole project. With that done, I soldered down a couple of resistors to help with noise in the I2C lines, and then was done with the main board. The parts are finally ready to be assembled now, so I started by getting the 3D printed left and right triggers on the frame. These pivot on that 2mm rod stock and have a little recoil spring on them to give resistance when pulled. These triggers are also using Hall sensors similar to the left stick. Hall effect sensors detect magnetic field strength of a simple magnet as it moves closer and further away from the Hall sensor. Because nothing is physically touching anything in a Hall sensor setup, they last a long time and are very accurate. In my case, they're also much easier to design around. For my triggers, I'm using these little 49E sensor guides glued to the frame and a tiny neodymium magnet for each sensor. I made a little calibration tool in Claude that detects the magnetic field strength for each sensor. I can get a value out when the triggers are at rest and when they're pulled all the way in. I enter those values I get from the calibration tool into my controller code, and that's that. I do a similar process for the Hall effect stick. Getting all the electronics to fit in place took a couple of tries. I would get the assembled PCBs in the frame and something wouldn't fit, or there would be some wire routing issue, or button contacts would be off. After enough issues piled up, I made a V2 update to the CAD, ran the frame through my Grasshopper definition again, and printed out a new version. Things fit mostly okay with the V2 set of prints. I did have to do some minor Dremel work, but generally everything had good clearance and fit with the wires routing through the frame just fine. For making the GST-SH wires for connecting all these separate components to the main board, I just ordered some pre-crimped plugs in a kit. This way I could cut the wires to length and crimp only one of the ends. Doing things this way cut my crimping work in half, which really helped with my general sanity. With that, I had all my wires routed and everything connected. I just snapped my back cover and front cover on the frame, and all the components are captured inside the controller. I did add a little on-off switch on the front of the controller. When this is on, the battery is powering the ESP32. If you turn the switch off, it'll disable charging when the USB is plugged in, or just turn the controller off when it's running wireless. With that, all the functional parts of the controller are done. You can see when I turn it on, it's appearing as a single discoverable Bluetooth device. When it's connected, it shows up as an Xbox controller and a mouse in the Windows Device Manager. As I move the controller, the onboard gyro moves the mouse cursor. It's just so awesome seeing this whole setup up and working. Back buttons all work as my normal mouse buttons, with left, middle, and right click. Holding the fourth paddle button suspends the gyro mouse input so I can recenter my controller in space. This gyro lock feature is similar to the motion of lifting a mouse and moving it over to reset its position on a mouse pad. I also have my fully working mouse wheel up here on my left trigger, and my forward and backward buttons embedded in the left and right sides of the controller. I can trigger these by just pressing my palm against the top of the controller body. Again, it's all working really well, and I can easily and intuitively use it as a functioning mouse right away. The Valence can also act as a fully working stock Xbox controller too. All the ABXY buttons and direction pad are running. The select start and shoulder buttons are all working great, and the Hall effect triggers and left analog stick are all calibrated. The touchpad's being picked up and it feels like it's in a great physical position on the controller. Right now the touchpad's in a stick emulation mode, This means that when I move my thumb around the pad, it appears as right stick motion on the controller. I'll dive more into this in a little bit, but the important thing now is that the touchpad tracking is all good. For me, the next part of the project is where things got really fun. I had a working controller, but needed to figure out all the little behavior details that would make it great. The first thing I noticed was the gyro's cursor speed was a little off. In some cases it felt a little slow, and in others it felt a little too twitchy. I had a leftover settings button, so I mapped that to change the gyro cursor speed. When I hit that button, the built-in NeoPixel LED on the ESP32 would blink once for low speed, twice for medium, 3 for fast, and 4 for ultra-fast gyro input. Next big thing to attack was the touchpad. To be honest, I wasn't sure exactly how to use the touchpad for this setup. So, like I mentioned before, I started with a simple analog stick emulation. This mode makes it so touching the pad would move a simulated right stick on my game controller. By adjusting the size of the center dead zone and the distance around the outside of the pad that acted as the max stick direction, I could change the way the touchpad to stick felt. This is all pretty neat, but if all I was going to do with the touchpad was emulate a gamepad stick, then it was a little pointless. I could have just left a normal stick in there. I decided to set it up so I could hold the A button and settings button to swap the touchpad between stick emulation on the Xbox controller to a trackpad mouse mode. This way I could set the touchpad to act as normal mouse control except with super high sensitivity, and then use the gyro for micro cursor adjustments. This setup let me leverage the best aspects of the gyro and touchpad for really smooth control. The final mode I decided to implement was an X-axis lock on the touchpad for FPS games. This setup is kind of a touchpad equivalent of a flick stick layout. This lets me swipe in a direction to quickly turn in-game, then aim with the gyro. Because the touchpad is locked to only track my left and right finger moves, all the vertical up-down aiming and micro adjustments are done with the gyro. I found I could use it pretty well in single player, but when I had to react fast in online FPS play, I get all flustered and not have the muscle memory to fall back on like I do with a mouse and keyboard. But again, this has more to do with my lack of gyro aiming experience than anything. Beyond that, I was really impressed with how easy it was to get it up and running. I've configured flick stick controllers in the past, and those require a lot of complicated tweaking in the Steam controller settings. Because the Valence was just acting as a normal controller and mouse, there really wasn't any special tweaks I needed to do to make it work in-game. I'm really excited to keep using the Valence controller and seeing how far I can push my skill level with it. I feel like I learned a huge amount about implementing more complex microcontroller projects on this one too, which was a huge achievement for me. I was thinking about open sourcing this design, but I have a lot of updates I already want to do, so I'm going to hold off on that for now. Looking forward to continuing development on the concept and exploring those fun ideas in a V2 design. Thanks for watching, and I'll see you next time.